Okay. Right, so we can start, right? So proving methods, what I'll be showing today is from a book called Introduction to Proving Methodology by Zhang, which is the introduction to advanced mathematics, in which we are kind of proving shit, right? Proving methods, which we will be studying today, will be like very obvious things, which I suppose if you're familiar with logic, you'll probably know all of them, right? There are referrals to like truth tables, there are like cases and things like that. So in the first part, like proving methods part 1, we'll going over trivial proofs, vacuous proofs, direct proof, proof by contrapositive, and proof by cases. This will not be anything complicated. So I hope you already know a lot of these, but yeah, let's start. The first thing we'll be showing is trivial proofs. So when we have a statement, an implicational statement that implies P implies Q, right? In which Q is true irrespective of the first part, the P of X being true, right? Showing that the statement is true in virtue of this methodology is called a trivial proof. So what happens is if the Q of X is true, in both cases in the truth table, we will get that implication is true. Right, it's impossible for Qx to be true by virtue of the showing this in the truth table, right? Let me just kind of employ like this and this to result in a false statement, right? And this is irrespective of anything happening in P of X, right? So this is called the trivial proof. An example which might illustrate how this behaves is very rudimentary, right? If we denote n to be a participant of integers, right, the set of integers, and if we say that n to the power of 3 cubed is greater than 0, then 3 is odd, right? We know that 3 is odd irrespective of the first participant, right, of the first participant. Then the statement is true because 3 is an odd integer, right? And the implication is therefore also true. This is very, as the implication says, professors in universities, if you're studying mathematics, professors might say that something is trivial. This does not imply that it is done via a trivial proof. It just means that they think it is so obvious that you can't miss it. So they can be referring to all sorts of different proving methodologies, or they can be talking about no methodology at all and just implying this as factual or true, irresponsive of anything, right? So don't confuse when you hear someone saying it's trivial to referral of trivial proof. It often happens in videos as well, like when you're studying mathematics and you're watching a video on YouTube or something, a lecture, and someone says this is trivial. It doesn't necessarily mean that they're referring to trivial proofs. The second part of this is called vacuous proofs. Vacuous proofs we show by the similar vein, and that is that if you have a statement in the form of implication, as stated as P of X implies Q of X, in which P of X is false for every X, that results in the implication itself always being true. You can see it again here. P of X is always false, right? The only two examples of P of X being false result in the implication itself being true. And if we can show that P of X is always false, right, for any or all participants X, then we have demonstrated that the implication is true, and we have done so via vacuous proof. So we can have an example of this, right? And that is that we let X be a participant or the element of real numbers, and if we have this inequality, then we have another inequality. You can read this for yourself. It's done here is that we are observing the first participant, right? And that is the first conditional of the implication. We observe that if we reduce this by 1, right? If we reduce this by 1, we get the cubic formula, right? And we know that cubics are always greater or equal to 0 for any participant X here, right? Of real numbers, not any, because we can get complex numbers. But for any real number, this will be greater or equal to 0. Therefore, what we do is that we use this cube and add 1. You can see very clearly that if you add 1 to this equation, you will get the first equation, which is greater than equal to 1, right? Because we have added 1 to both sides of the inequality. And 1 is trivially, not by trivial proof, but is obviously greater than 0. And thus we have that the initial statement is always false, right? And what we have shown is that the implication then is true. Again, this is very, very simple things. It's not actually used anywhere. I have tried to look over my textbooks and things to find the examples of trivial and vacuous proofs, which would be useful, so to say, in some more complex mathematics, but I was unable to find them. It's mostly used if we have a vacuous or a trivial proof. It's not very interesting, and therefore it's rarely presented in the literature, right, as far as I'm aware. It's mostly used when you're so obviously inferred that the presentation or the problem you have been given just has a problem, right? It's usually meant when someone says it is vacuous or it is trivial, it's shown, it's proven vacuously or it is proven trivially, that it is a faulty presentation, right? It doesn't mean that the implication is false, quite to the contrary. It just means that it's uninteresting. A more useful way of showing things is called a direct proof. It is done more often, but I still wouldn't call it something which is prevalent in literature, or is done in conducive or in concert with a lot of things, right? It's just a useful way of seeing things differently, right? What is a direct proof, right? If we have an implication, again, we're talking about an implication which is true for every x participant of S. And S is the set which is examined, right? P of x would be like a property or something which would be relational or operational over the set of S, and x is just an element which is in that S. What S is kind of inconsequential to the methodology we have here. So what we do is we assume that the P of x is true for an arbitrary element of x, which is still an element of S, and show that Q of x must be true as well for that element of x. We have to be very careful here. The reason we must be careful is the arbitrary here doesn't denote things which we might intuitively think as arbitrary. So when you have a set of things, for example, 1, 2, and 3, right? A set of 3 things, 3 numbers, 3 ordered numbers in this case, 1, 2, and 3. It wouldn't be arbitrary to just say 2, right? It would be arbitrary in how we use the word, but in virtue of doing a direct proof, you cannot just pick an element. What is done will be maybe shown better in an example, which is following. But what is done is that you take a representative. So for example, you take n to be an element of this set. Now what that element is what the arbitrariness of the presentation here is referring to. Am I making sense? Does anyone have a question regarding this? Maybe? I'll take that as a no. So what's the reason for taking px to be true, right? Why are we doing this? Because as we have seen previously in vacuous proofs, if this is false, then we trivially get to the we trivially get to the implication being true. So we have what we want to show is that it cannot happen, that this thing here cannot happen. This is what we want to show. So we take an element of the set we are examining, this is S in our case, and we are showing that in this case, this line here is impossible. Maybe this is here is just presenting this in a more structured way, in a more strict way, how a mathematical presentation would be if we are strictly going by the virtue of discipline. But what is essentially being done here is what I have just described, right? we are trying to ascertain that this here necessitates this line here and not the previous one. Okay, now we get to an example to show exactly what is being meant by the direct proving method. For example, if n is an odd integer, then 3n plus 7 is an even integer. Now, I would like, here are some important notes, especially the ones I have bolded, right, reddened here, to define things which we'll often be using in this presentation. So keep in mind what we mean, why this follows, and things like that. If you have any questions here, I'll be glad to answer. Just a small notation. In general formulation, k here is just a placeholder, right? And we are taking k to be an integer. In more strict formulations, for example in sequences, when we're searching for a sequence, which is most often what we will be doing in direct proofs, you will not be taking k to be an integer, you will be taking it to be a natural number, so a participant of n. And an even number would follow the same thing. K here is denoting a placeholder symbol. It doesn't actually mean anything except that it's an integer or a natural number. So these are important things to consider, right? Does anyone maybe have an idea how we would go about proving this example over here? You can unmute if you have something to say.
Actually, since this is the debate room, everybody is forcibly muted, so you're going to have to manually unmute them so they can talk.
Oh, okay. Well, you can you can ping me if you have anything to say or want to engage here. Any questions presentable or something in the debate event chat, right? And then I will unmute you. It seems that no one has an idea yet. Okay, that's fair. What will be? Maybe I haven't given an example of this, so maybe this will serve as a sort of presentation of what is being meant. So this is a general solution, right? We're taking to know that the first part of the implication is true, right? We're assuming that n is an odd integer, so we are assuming the correctness of the first participant of the implication. Since n is odd, we can write n as being equal to 2k plus 1 for some integer k. And this follows from there, right? And we define integer n to be odd if this. So we have only inferred the fourth important note here to present what we mean. Now what we do is we take the second part of the implication, 3n plus 7, and use the information we have previously ascertained or assumed for an n, and change the n to be representative of this, right? So instead of n, we're using 2k plus 1, and then we're just using simple arithmetic, simple algebra, and we get to the result of 6k plus 10, which is both of these participants are divisible by 2. Then we take 2 out, make the equation like this, and now we see that we can ascribe this to be u, right? Anything. Because k is a placeholder, since we know that 3k plus 5 is an integer, right? The multiplication of an integer with an integer is an integer. The addition of an integer with an integer is an integer. We get that 3k plus 5 is an integer. If you want to ascertain that this is an integer, usually if you want to have a very strict proof of this, there are proving methods in like strict analysis, but generally it's uninteresting. Here we're just using this as a sort of showing of the methodology, not the actual rigor in this example, right? So what we do here is we show that this is then equal to 2u, where u is some integer, right? And that is of the same formulae as this here, which means that 3n plus 7 is even. Any questions? not. Right? Okay. Since there are no questions, I'll take that this is understood. Then we're going through the next part, and that is proof by contrapositives, or maybe on exercise 1. You can. I think that since nobody's engaging really, that this is just another example of how we can do this. Show that the following implication is true, right? And if an n is an odd integer, then 4 times n to the power of 3 plus 2n minus 1 is odd. The first solution, we have two solutions here to kind of show how different how we can think of this differently. It is to do the same procedure we have done previously. This y here is the same as k. It's just a placeholder. The only condition we kind of have to keep in mind is what these placeholders refer to. So if we would have like two unknowns in this equation or something, right? If we were to have an equation with two unknowns and we want to use two placeholders, we have to be careful if we have to or don't have to use the same notation, right? Or different notation. This follows the same principle. What we have done is we have just changed in the equation, did the simple arithmetic here, and gotten this ending result. This ending result, like this here, is, for example, u again. And since this is in the formulae we have previously stated as being odd, then the whole formulation is odd as well. The other way to go about this is that this is a polynomial. And since this is a polynomial, we can think in a kind of a different way. And that is that we can observe that if we take 2 out of this, right, we expanded this by 2, it doesn't change anything. This is minus 2 plus 1 is minus 1 here. And if we take 2 from this, we still get this formulation, which gives us the same result. We just skipped all this algebra, all this arithmetic. It gets to the same result. This is still u. Maybe u1 here, because we don't want to confuse you with this u. And we get that the only thing you have to be careful of if you're in some maybe more complex situations is that is this thing here, the u which we have defined here, we have placed as u equaling this equation, is this part, like, which we are depicting as u, truly an integer. We know that multiplication of an integer is still an integer, and summation of integers is still an integer, so this follows, right? You can even operate in different fields, for example, and different fields would be having different operations of addition, and in those fields it is quite possible that u would not be satisfied as an integer, and then this wouldn't follow. But generally, I think that the methodology here is quite clear. Any questions? Okay. Then what we do then is let's take a look at a different proving method, and that's contrapositive. A contrapositive is kind of a different viewing of a direct proof. So a proof by contrapositive is a direct proof of the contrapositive, and a contrapositive is this, right? Not q. You can also depict this as being m of x implies n of x here, right? Doesn't change anything if you depict m of x to be not q of x. So the same thing is here, just maybe this helps in understanding. So this is a direct proof, but very unique looking at a direct proof. An example of this is, let's take this example. Let x denote an element of integers, then 11 times x minus 7 is even if and only if x is odd. What we have here is very unique, and we will talk about this in the next proving method, and this is if and only if. if and only if part. If and only if part. And that, I think you know that this is the notation of if and only if, and it means like having the implication like this and the implication like this, and right, this is the same thing. Now we get to the solution. Since there are two implications, we have two cases. The first one is if x is odd, then 11x minus 7 is even. This is a direct proof, so if you want to do it, you can. It's simple. And the second implication is 11x minus 7 is even, then x is odd, which is the converse of 1, right? What we can use here is the proof by contrapositive, even though we don't have to. It's just for the depiction. Assume that x is even, right? Assume that that x is even. Then we can depict x to be 2s, where s is an integer. Therefore, 11x minus 7 is 11 times 2s minus 7. We do the simple arithmetic, get to this. This is the formulae of an odd thing, since we can also depict this to be like something, right? We can depict this as a big M. And this will result in us finding that 11x minus 7 is odd. However, we have used the proof by contrapositive. That means that we have shown not q. And the negation of 11x minus 7 is odd, is 11x minus 7 is not odd, and what isn't odd is even, right? And then, since this is a kind of a binary thing, you get to have that this implies or leads to 11x minus 7 being even. And this is what we wanted to show. So both implications are true, and that means that the equivalence, the relations of equivalence, is also true. Okay. Now we get to prove by cases. This one is actually very prevalent. I think that this is the most common way of proving things within mathematics. You can use it for definitions which have like multitudinal properties, which have to be satisfied in order for a depiction to be ascribed correctly. You use it for equivalences, as we have seen in the previous example. You can use it for anything which actually has multiple things which needs to be proven in order for the depiction to be true. This is a way of saying this, right, in a more rigorous manner. Sometimes it may be useful to infer subcases. I'm not familiar of any presentation within mathematics which actually depicts subcases. Usually it's the cases within cases, right, which is by definition subcases, but no one actually denotes it like that. Usually what the use of subcases is in programming, when you have like a lot of complex things. But in general mathematics, when you're not programming things on a computer, you'll not encounter anything very complex which necessitates the distinction between cases within cases and subcases. General methodology for subcases and cases is the same, so there is not really much of a difference there. It's just aesthetic, right, organizational. Let's take an example of this. If n is an integer, that this statement, this n squared plus 3n plus 5 is an odd integer, right? The first intuition, since we're talking again about odd integers, is one might infer that we will be using something that we'll be talking that why do we need cases here, right? We might infer that this is just a direct proof or proof by contrapositive, which would be a false thing because we don't actually know how n behaves here. But the intuition kind of guides us to what the actual way of proving this implication might be, and that is that we will be using the statements of what it means to be even and odd, but we will have cases. The solution will then imply cases. The first case is when n is even, and the second case is when n is odd. The methodology here is the same, so this is already something you're familiar with. And the methodology is quite known right now, right? And it results, in both cases, it results in showing that this equation here, this statement here, is indeed odd, irrespective of n being either even or odd, and this is what we wanted, and therefore the cases show, we have proven that this is true by virtue of cases. Although this also uses like a direct proof, right? And yeah, that's pretty much it. So methodologies kind of intersect when you need them to. Cases is the most famous one. Usually when you're talking about cases, you will encounter a lot of different proving methods within them, because you have to prove the cases, and if you want to prove cases by cases by cases, you'll just get into this infinite line and you'll never prove anything. So you kind of have to rely on previous methodologies to get to cases. But cases is very important because this gives us a dichotomy here. It gives us a binary relation that n is even, n is odd, and if you prove both things, you have proven that irrespective of n, we get the odd integer, which direct proofs can't do. That they cannot do an irrespective thing, they do respective things. That means that n, respective of the formulation of n, this is true. But since we do not know the formulation of n apart from like the participation in integers, which is not enough for a direct proof, we have to infer cases. So the motivation for cases is such so that we can prove things. Sorry, we can prove things which are irrespective, and that's a big draw of it. The other one is this is a more general presentation. This is an example which might be a bit more technical here, because we'll be using different things, and I'll be introducing another thing with this example, and that is the vlog thing, which is without loss of generality implication assumption. So, well, let a and b be integers, right? Then a times b is even if and only if a is even or b is even. The thing which we always have to be very careful of is this one. It's if and only if. This gives us the need for the cases, and that is the implication of the right side from the right side and the implication from the left side. So let's first go the implication from the right side, and that is if a is even or b is even, then a times b is even. Now we have a is even and b is even. Without loss of generality, or however otherwise presented as vlog, it means that we can take a to be the representative, because the taking of the representative doesn't actually matter to the proof. Maybe an intuitive presentation of how to think about this is with Bayetto diagrams, right? Because we have an OR, we're talking about everything here, right? We're talking everything in these two sets. And if we take a participants, let's say this one as being RA, that is the A we're taking here to be even. The maybe more perceptive among you may think like in subsetual terms, like if we have A like being this, and then every A is in B, so every A is also a B. But this is uninteresting because then we are just taking B instead, and it doesn't change anything, right? Usually without loss of generality is not implied before you conduct the proof. And when I say proof, I mean the proof in which without loss of generality is implied. So not the whole proof, but generally just the proof in which it is implied. So if we didn't know how we would conduct the proof, or if it was necessary for a B to be proven as well, in a disanalogous way, so that the proving of this would be disanalogous, that the same methodology for A doesn't apply to B, then without loss of generality wouldn't be implied, and what you would need then is another sub-cases or cases, however you want to think about it. What is done here is that we are taking a to be representative as 2x. This is from that important notes at the start. Thus, the multiplication of a times b is 2x plus b. We can denote, we extrapolate 2 and get this. Multiplication of two integers is an integer. We denote this with y, for example. And then we get the general presentation of what it means to be odd. Since xb is integer, asb is even. We have shown this implication, so the right hand side implication. Now we get to the left hand side implication. Assume that a is odd and b is odd. What we're kind of denying, what we are kind of using is the negation of this. Does anyone know what does that mean? What method are we using in the converse here? It's a method which we have already examined. It seems okay, then I suppose that no one does. This is proved by contrapositive here. We have negated the left-hand side implication as contrapositive. So we are taking not this, right? This implication we are negating. So A is odd and B is even, odd as well. We are doing this by De Morgan formulas and getting the result, right? What is being done now is the same proving method, right? The proving by contrapositive. We're implying that these two things are like are odd. We're putting general presentations of what it means to be odd. We know that x and y are integers, and hence we have the general multiplication. So we're just using the general algebra, right? Multiplying, adding, and doing stuff like that to get to the concluding formula like this. And this formula is obviously constructed like in the presentation we have usually defined as odd. However, since we are in a proof by contrapositive, this actually means that we have shown that a times b is even. And this is what we wanted. Because this is not q, and this is therefore q, and we want this, we want q. And this is the example, right? Does anyone have any questions about, without loss of generality, maybe the converse methodology implied here? I suppose not. Well, now we are at the end. I didn't clear this. F. Well, yeah, so this was supposed to be press delete to. Okay. So now we are starting polling, right? In this right hand side you see the ID. So if you want to go to the app, push the ID in. You will see on your phone the question presented, right? You can either view it from your phone, right? The question is posted then there, or you can view it from the presentation. It seems that I'm the only one in, so what is being questioned here is you kind of have to infer. So this the question itself, up until the part which of the following is proved above, is a proof. And what is being questioned here is which of the four statements this proof proves. So let's take it step by step, because it seems that no one is doing this. Is 3n minus 5 is an even integer proved by the proof above? No, it isn't. Why isn't it proven? We have shown that 3n minus 5 is even, so how come we haven't shown this statement to be true? Because we have shown that 3n minus 5 is even if n is an odd integer. We have not actually shown for what it means for an even integer. So if we wanted to show the first claim, right, that the 3n minus 5 is an even integer, we would have to infer that it is true by virtue of both cases, even and odd, or some other positive and negative, or something like that, right? Since we have not done that, we have just shown one of these cases, we have not actually inferred that 3n minus 5 is an even integer. What about the second claim? If n is an odd integer, then 3n minus 5 is an even integer. Well, yeah, of course. We assume that n is an odd integer. This is as if we are assuming the first participant to be true, and then we have shown that the conditional is true by virtue of what is this proof? Is this direct proof? Okay, well, this is obviously true, right? Yeah, this is a direct proof, right? Let's look at the third one. Let n be an integer. If 3n minus 5 is an even integer, then n is an odd integer. Well, this is reversing the actual presentation. We have to be careful here, because it might be playing a trick on us. We might be talking about contrapositives. Now let's run it back a bit. What does contrapositive actually state? A contrapositive of these statements. So if we taken 2 to be true, right? This is true. The contrapositive of that would be not this, right? Not 3n minus 5 is not an even integer. So that would be our first implication. And we see that 3n minus 5 is an even integer here. But it's even in a positive sense. It's not a negation. And therefore it cannot be a contrapositive of the statement. And since it cannot be a contrapositive of the statement, we know that this doesn't infer to a contrapositive proof. And now we can just look at the implication. 3n minus 5 is an even integer. Okay, does this mean that n is an odd integer? Well, it actually doesn't, because we have assumed that n is an odd integer here. That means that we are taking the implication in another way. We are taking the right-hand side implication. This would be a left-hand side implication here, from the initial one, right? So if we take 3n minus 5 to be an even integer, that what would that even mean? That would mean that we can converse this as 3n minus 5 times 2, right? So we would have this. And from that, we would have to infer that n itself is an even integer. And we have not done so. Let's try the fourth one. And this one is obviously a contrapositive. And since it is a contrapositive of the statement we know to be true, then it's also true. And done. Let's look at our graph. So is this true? So our answers were 2 and 4. Everyone, that means just me, has answered with 2 and 4. Is this correct? It is. And this concludes our presentation. This is proving methods number 1. We have not done anything complicated here. We have not done anything particularly engaging, because the only one which is useful are direct proofs, proofs by contrapositive, and proof by cases. but this serves as a solid introduction to the general proving methodologies within mathematics. The next one we will be looking at the existence proofs and proofs by contradiction, and the big one, and that is mathematical induction.